Okay, thank you, Stephen. Thank you for the introduction. Thank you to all you guys for making time this afternoon to learn a little bit more about Liqid, and thank you to the Dell team for hosting us this week. It's been a great show for us. So I'm Sumit Puri. I'm the CEO and co-founder of Liqid. Liqid is a company in the software-defined infrastructure space. Our mission in life is to turn the data center from static to dynamic. The technology that Liqid has been developing is something referred to as composable disaggregated infrastructure, and we'll explain exactly what that means in a couple of slides here. The main problem that we're looking to address in the data center is around resource utilization. If we take a look at the data that's out there, the hardware utilization rates of the devices that we're putting into the data center are very low. 12–15% is the average utilization rate of hardware being deployed in the environment. We take a look at things like hyperconvergence and virtualization, and those have been very powerful methods for us to increase the utilization rate of the hardware that we're deploying. Our belief is composability is the ability to take that utilization rate to the next level. If we take a look at where the data center has evolved, we've evolved from what we refer to as traditional three-tier architectures, where there were actually fully static configured boxes deployed into the data center. Today, the big buzzword is around things like convergence and hyperconvergence. Companies like Nutanix have made a big impact in the industry with their hyperconverged solutions. VMware is an amazing solution that allows you to virtualize. But if we think where the industry is headed, our belief is disaggregated elements in the data center and then composing servers based upon those disaggregated pools is where we see the industry headed. This is a chart from Gartner and talks about how the industry is changing from static to dynamic. Last year, Liqid was awarded the Gartner Cool Vendor Award for our work in composability. So what do we mean by composable infrastructure? Composable infrastructure is a new way of building servers in the data center. With composability, we don't take devices and plug them into the sockets of the motherboard to define our machine. It's all about pools or trays of resources. Imagine a tray of storage, a tray of GPU, a tray of compute, a tray of networking devices, a tray of FPGAs. All of those resources, instead of plugging those into a motherboard, we plug those into a fabric. And then we come in with software and we orchestrate or we compose at the bare metal. Grab this CPU from this tray, grab me those 4 SSDs, those 6 GPUs, and build me a server. Just like we were plugging in the motherboard, except we're defining it in software, and on the other side, we're getting delivered physical infrastructure of any size, shape, or ratio. And the more important part is that infrastructure is dynamic. When I need another GPU because my workload has changed, we don't send a guy with a cart to power down devices. We just reprogram the fabric and dynamically add or remove the elements based upon what's happening at the application layer. So what we provide for composability is the software that allows you to orchestrate and some technology that allows you to interconnect your standard off-the-shelf hardware. One of the use cases that we're working on, a POC that we have deployed, is with a transportation customer. And if you can imagine the transportation business, what happens at 5 p.m. is very different than what happens at 2 in the morning. And right now they play a game of workload matching. If a small workload lands on a small server, everyone's happy and the world is good. If a small workload lands on a large machine, they're wasting tens of thousands of dollars of hardware that's going underutilized or not utilized at all. So they said, we want to take a new approach. We want to study the workload as it comes in, dynamically make a decision on whether it's small, medium, large, extra large, 2x, whatever the workload needs, get the workload done, and as soon as the workload is done, free the resources back into the free pool and let somebody else have at it. If we can take the utilization rate of this hardware higher, we think we can impact the TCO argument inside the data center. And for this customer, it wasn't even a question of, am I going static or am I going dynamic? They know that static is better. They know static is not as good as dynamic. They know dynamic is where they want to be. For them, it was a question of, am I going public cloud? Am I going Amazon to AWS? Or am I going on-prem? And so what we offer with composable technology is the ability to get all of that flexibility and agility that you get from public cloud, except we give it to you on the hardware that you're responsible for. A 8 GPU instance in Amazon cloud, that is not an inexpensive solution to lease or rent. It's very easy. It's the easy button. Put a few keystrokes in and get the machine that you want. but the cost associated with that is significantly higher. So what we say is we can give you that same flexibility and save our customers a ton of money doing it, right? Not all workloads are moving to public cloud. There's this fallacy that everything's going to public cloud and no one's ever going to own infrastructure any longer, right? Dell sells something like $70 billion of hardware a year. Most of it is not going to the big five hyperscale providers out there, right? There's still a tremendous need for on-prem infrastructure. If you're a bank, for example, you're not necessarily going to put all of the bank records up in public cloud. If you're a healthcare company, there's regulations. You can't just dump everything into AWS. So what we believe is a bimodal environment is where the future is headed. Some amount of your infrastructure will live on public cloud. Some amount of your infrastructure you're going to be responsible for. And for the infrastructure that you're responsible for, we want to give you the tools to get better utilization out of that hardware. Another deployment we have is actually in Southern California at one of the studios. And this is a very simple use case to understand. They use some NVIDIA GPUs, the V100 GPUs. These things are very expensive, $10,000 a pop kind of thing. So they have 4 of them in a box, so roughly $50,000 worth of hardware. During the day, they compose those GPUs to the AI engineers and let the AI engineers use them for their workloads. At night, when those guys go home at night, they reprogram the fabric and they give those GPUs to the video rendering machine. Out of the same $50,000 worth of hardware, they're able to get 2x utilization, right? That's a big knob, right? As far as hardware goes. The only other way to do this is have dedicated GPUs for each of those environments. What we give the customers the ability to do is say, hey, those guys went home at night. Why are those $50,000 worth of resources not being utilized? We give them the ability to go off and utilize those resources better.
So you say that most of your customers are more in the repurposing of the infrastructure instead of fast provisioning.
It depends, right? It depends on the use case. We're a flexible environment. Some customers are benefiting from the flexibility of being able to reconfigure machines because that's what they can get better utilization. Other customers are cloud service providers. Their business is to offer cloud as a service. So if we can give them the tools to make things dynamic and composable, their entire value proposition is built around the TCO model, right? So we can give them a better environment. The other interesting thing is there's certain scenarios where composability allows you to do things that you just couldn't do before. Dell, one of their main servers that they sell is the Dell 740. Inside of a Dell 740, I can maybe put 2 or 3 GPUs inside of it. With our solution, we can take a standard Dell 740 and start putting 8 or even 16 GPUs inside of that machine. So I can now create configurations that weren't even possible before. I can solve problems that weren't even possible. The other benefit is the power of disaggregation. What do we do today? Intel releases a new CPU. We take the data from the old box and we put it in the new box and we throw the old box away. Rip and replace is the kind of normal model that we have. Probability is your networking was fine. Your power supplies and your fans were probably fine. Your SSDs were probably okay also. Why are we throwing away all of this infrastructure just to get one new element inside of our environment? With disaggregation and composability, I can remove that tray of CPUs, put in the new tray of CPUs, and not change the rest of the infrastructure. So by disaggregating, we're going to be able to, again, affect the total cost that these guys are incurring to deploy this hardware, right? So it's the answer is mixed depending on what you're trying to accomplish, right?
So, what's your current mix of public cloud providers versus
yeah, most of what we're doing today is customers doing on-prem stuff, right? There's some mix of cloud service providers who are looking at our equipment and trying to figure out how they can best use this in their world. But right now, most of what we're doing is a lot of on-prem, right? But there's a lot of clouds being built on-prem. Not every cloud is being built by a cloud service provider. Big companies like Equinix, for example, they make their entire business of providing connectivity, power, and cooling so that people can put infrastructure in those environments, right? So right now, a lot of it on-prem, but we're moving all over, right? Everyone talks about software containers, right? It's like the new preferred way of putting software out into the data center. What we enable in our platform is this concept of hardware containers. If I'm deploying something like a tensor workflow container, for example, I probably actually know the perfect hardware that I want to deploy on that software. So even though I have 50 pieces of hardware in my rack, I can configure 200 different machine types. So what we do is the ability to create templates, save those templates off, and at a later time spin them up. One click, launch the hardware container. The next click, launch the software profile to put onto that machine. So this idea of containers doesn't only apply to software, we're making it apply to also physical infrastructure. AI is a big thing, right? Everyone's talking about, AI is that next generation workload. The new compute of the future may not be x86. The new compute of the data center may be things like accelerators, things like GPUs. These are critical for determining how AI algorithms are going to work. And if we take a look at what AI is not an event. AI is a workflow, right? First thing we do is we ingest our data. That's a lot of networking capability that I need. Then the next thing we do is we clean our data and we tag our data. That's CPU intensive. Then what we're doing is we're running training. For training, I probably want multiple GPUs, the biggest kind that I can get, to crunch through my training sets as quickly as possible. And then after training comes inference. And that's a different kind of GPU. It's a low-cost GPU that's going to be deployed out in the field somewhere. And at the center of all of this is data, right? Why are we moving large sets of data around from machine to machine for the different phases of the AI workflow? We think that doesn't make any sense. We think data has gravity. Let's leave the data at the center of the universe. Let's bring the networking to the data. Let's bring the GPUs to the data. Let's bring the CPU to the data. That's much easier, right? We have a customer right now who's in the seismic space that they're talking to us, and they have an ingest engine that sucks in a petabyte of data. And then they copy that data off to worker engines over a 10 gig link. That data copy can take an entire day sometimes. In our environment, what do? They just recompose the data and move the entire tray of data to the server that needs it. We can recompose that in 30 seconds and give them time back.
AI pipeline, as you call it, or workflow.
This is called a composable AI platform.
Can you automate this? Can you put in the policy?
Yes, so that's we'll get to that in a second. But yeah, absolutely, policy-based management is part of the whole thing. Higher level orchestrators controlling the fabric is this is how it's designed to work. We have 3 ways of controlling our fabric. You can come in through the command line and bash on the command line. We have a very intuitive GUI that we'll show you guys here in a second. You can use the GUI. But in reality, customers at scale, they're going to be using our API. We got a REST API, and you can program against that. So higher level orchestrators will be controlling our fabric, whether that's Kubernetes, whether that's Ansible, OpenStack, Puppet, Chef.
So you can actually put like functions and so on, and if a certain event happen, you can trigger part of the policy.
That's right. So that's where we get into policy-based management, right? So when you create your machine, set up a policy that says at 10 o'clock at night, I know no one's using those GPUs, automatically reprogram the fabric and reallocate them over there. Set up a policy that says when that server goes above 80% of the storage utilized, automatically reprogram the fabric, give me more storage, right? So policy-based management is happening today. The next phase is autonomous, right? It's the AI portion of it, right? Let the AI algorithms study the usage of the hardware inside the data center. Let the AI figure out where resources can be reallocated, right? That's the future. We're not there yet, but the long-term vision of this thing is the lights-out autonomous data center where things are automatically being moved around based upon the AI algorithms that you guys have implemented, right?
Okay.
So that's the future. We're not there yet. This is a journey, right? So we're on that path, right? Yep. So today it's about user defined. Next will be about policy driven, and in the future we move to AI based. Right? So it's AI controlling AI, right? It's the machine building machine. The Skynet scenario, right, is coming, right?
You're talking about very good level of granularity. I mean, you can have multiple CPU assigned to the same machine. What about the SSDs? So can you have less than one SSD for a machine in terms of size, maybe protected?
Yeah, so right now what we're doing is around physical bare metal composability. So when I give you an SSD, I'm giving you that entire SSD. The holy grail use case, I'll be honest with you, for composability is hyperconvergence or virtualization built on top of composability. Imagine if the hyperconvergence or the virtualization layer could reach down and say, I'm out of storage to virtualize on top of, give me more disk. I need another GPU because my vSAN workload needs it, give me another GPU. So we believe virtualization, hyperconvergence deployed on composability is the holy grail, right?
I was going to ask this later because I have a feeling you're going to get into it, but a common theme in the composable world seems to be that the composability, the element of composability for compute is a single x86 server. Can you talk a bit about what the barrier is to achieving true composability with respect to memory and CPU, and whether that would even be something that would be desirable?
Yeah, that's a very great question. So let me be very clear. One thing we don't do today is I don't take a CPU 1 and a CPU 2 and munge them together to create a big, large CPU, right? That's not what we're doing, right? You can have a single socket CPU, you can have a dual socket CPU inside of your fabric, and then you can pull in the appropriate compute element that you need. The munging of CPUs together to create a larger CPU, that's not where we are operating.
Or how about memory, dynamic allocation of memory?
DRAM is DRAM is the only element of, so if we take a look inside of a server box, minus CPU to CPU and minus CPU to DRAM, everything in the box is speaking a common language, and that's PCIe, right? So number one, we can't munge CPUs and we can't disaggregate CPUs, and we can't disaggregate DRAM yet. DRAM disaggregation will come when we get to something called Gen Z, right? Gen Z is still a few years away, but that's when we're going to get the opportunity because the bandwidth and the latency profile will be there to disaggregate DRAM. Today, the way that we're solving that is we're disaggregating Optane. Right, so we're disaggregating storage class memory. So you can have a tray of storage class memory in your environment, and then you can compose as much storage class memory as you need, and then you can run it as either fast NVMe or reasonable DRAM. Right?
What's the trade-off in performance if you do that? It seems like if you're disaggregating the RAM from the CPU, there's got to be a hit.
Yeah, so Optane is not RAM, right? Optane is storage class memory, so that's why we can't disaggregate DDR yet, because the interfaces aren't available to make that disaggregation happen.
Right, but you said that when you get to Gen Z, you would be able to do that.
Yeah, so Gen Z, you know, the promise is that we start to approach DDR type latencies. Jury's still out, right? We'll see how this is still a future tech, but that's where they're intending it, is get the latency low enough. It won't be as good as DDR, but it'll be good enough. Right, is the theory. The jury is still out. PCIe Gen 3 is running about 150 nanosecond latency. PCIe Gen 4, we're going to chop that down to about 100 or sub 100. When we get to Gen Z, they're starting to talk about 20, 30, 40 nanoseconds of latency. And at that point, it starts becoming interesting, right?
What kind of redundancy do you have
on our solution? Yeah, we can talk about that. I have a slide. So let's talk about what the hardware actually looks like, right? So it's great to see the theory, but let us show you exactly the practical implementation of this. So what Liqid provides and what Liqid builds is the fabric switch and the software that lives inside the fabric switch. What we don't build is you guys know the term JBOF, just a bunch of flash, or JBOD, just a bunch of disk. Everyone's familiar with that. So that's just a box with PCIe SSDs inside of it. So that's a JBOF. We have a JBON, just a bunch of networking cards, a chassis with 24 networking cards across the front. Then we have a JBOG, just a bunch of GPUs. And in our world, compute is DRAM and compute element combined together. We take a host bus adapter, plug it into the server, connect it to our fabric. All of your devices live in expansion chassis or trays, and they connect into our fabric. So what you see on the screen here is a fully disaggregated rack. My tray of networking cards, my tray of storage, my tray of GPUs, my trays of compute. Even though that's a Dell 640 1U server, I can give him 4 SSDs and 3 GPUs and 2 NICs, and he's going to feel like all of those devices are locally plugged into his motherboard, and he will not be able to tell the difference for a simple reason. The latency through my switch is 150 nanoseconds. If I have a response time from an NVMe SSD that's measured in 100 microseconds, your 150 nanosecond latency will not even be able to be measured, right? So this is what a fully, truly disaggregated stack would look like. So here we are not disaggregating DRAM. The industry's not ready for that yet, but all the other resources can be disaggregated.
So usually you suggest to your customer to buy 2-socket servers. or does it depend on
it just depends on what the customer is trying to do. We can take a single socket, for example, take a single socket epic, and to that attach as many devices as required, right? One of the reasons people sometimes go to dual socket servers is so they can have that additional PCIe connectivity. What we can do is we can take a single socket server and attach as much devices as you want to that, right? I can't buy a server box today that has 16 GPUs inside of it, for example, unless I'm going to spend $500,000 on DGX2 or something like that. But I can compose a Dell server with 4, 8, 16, as many devices as I need. And I'm not bound by the physical PCIe lanes that are going in and out of that root complex.
In terms of rack optimization, so you could decide to go with a different form factor instead of the one rack unit.
We are completely hardware agnostic. One of our hallmarks is we do not try to tell the customer what SSDs to buy, what network cards to buy, we don't care. We're a software company.
Now
right?
the question is more, how many ports do you have in the switch to
Sure.
make it,
Yep, absolutely. So each one of these switches is 1U tall, half U wide. So in a single 1U space, we can deploy 2 switches so that we can get HA capability, right? And we can dual path and redundant path everything if that's what your environment requires. So in a 1U space, we can put 48 ports of Gen 3 by 4. Or you can do 24 ports of by 8 or 12 ports of by 16, whatever size pipe your customer, our customer requires, right? So it's a very flexible architecture in that manner, right?
For the compute side, any plans for EPYC or even ARM?
Yeah, so if you go to the show floor and stop by our booth, we're running EPYC on the show floor right now.
Okay, or
right.
ARM.
We've looked at it. We can make it work. So we've even integrated things like Jetson. Do you guys know what the Jetson module is? And then Xavier. So Jetson is the small GPU inference module that NVIDIA has put. It's a very small form factor GPU. The problem with that is it doesn't have any storage and it doesn't have any networking capability. So now we can deploy banks of Jetsons, for example, and compose in networking cards and compose in NVMe straight into the Jetson. So ARM is doable. I'll be honest, I don't see a lot of demand in the data center yet.
Oh, yeah.
So it's been a dream for a while that ARM in the data center is going to be important, and when that happens, we'll be ready. We're completely agnostic, right?
Cool.
It doesn't matter to us.
So what happens if I have different GPUs? Can I mix and match?
Absolutely. We have customers who inside of a single tray, because they're building clouds for their internal customers, they'll throw V100s, they'll throw P100s, they'll throw some T4s, they'll throw some RTX in there, and they'll just assign out whatever is needed by their internal customer, right? Yeah, so we don't care what type of GPU, we don't care what type of FPGA, we don't care what kind of SSD. It doesn't, listen, it's hardware. There's always has to be testing and verification and validation that everything is working as expected, but everything is speaking a common language here, so it just works, right?
So are you reducing it to a common language?
PCIe. Right? PCIe is that common language. I don't have to do anything. We have actually a data center first here, right? This is a kind of data center history here. And by no means, guys, are we tied only to PCIe. And we're going to get into one of the announcements that we have is, we can do multi-fabric. I can have a PCIe fabric. I can have an Ethernet fabric. I'll grab my PCIe devices. I'll grab my Ethernet devices, and I'll compose them into the same machine. But the important thing is here, we're at a data center first, right? For the first time in the data center, when NVMe storage migrated to PCIe, everything was speaking a common language. Where do networking cards plug in? PCIe bus. Where do GPUs go? PCIe bus. Where does storage go? PCIe bus. Everything is on that common bus, right? That's what allows us to compose at the bare metal. That's why we can do things like PCIe peer-to-peer and allow these devices to talk to each other, because I didn't create this language. This was the language that the computer architecture has selected as an industry, right? This is it. So that's why, when we started this thing, we said PCIe is that common thing that allows me to build composability at the bare metal. Our belief is composability without bare metal and composability without disaggregation is hyperconvergence. So anybody who's doing composability and not disaggregating, anyone who's using a hypervisor to chop and slice up stuff, that's just hyperconvergence or virtualization. That's not true composability, in our opinion, right?
One of the things you said before, you said that that the holy grail of composability is to be able to run hyperconverge and to have the hypervisor get whatever it needs on demand. Do you really think that the holy grail of composability is to, let's say, extend the life of the hypervisor, which is, in a way, virtualization is kind of extending the model of legacy applications, free-tier applications somehow? Don't you think that composability goes beyond that, beyond virtualization somehow?
I think they can live in harmony together. Our belief is virtualization will run better with composability. Our belief is, yeah, in some cases, because I can compose, I no longer need to virtualize. Yes, there are some use cases for that. I believe, though, there'll be a lot of use cases where virtualization will be used in combination with composability, right? We're not trying to replace VMware. We're not trying to replace, KVM and other hypervisors out there. What we're saying is there's a better way. Think about VMware for a second. I'm sure there's people that are not going to like to hear this, but the way that VMware or Oracle or SAP or any of these guys charge, they charge by CPU, right? They charge by x86. When my virtualization server runs out of a resource to virtualize on top of, what do? I buy another x86 processor so I can get some more resources, and as soon as I do that, I pay for another virtualization license. So not only are we going to increase the utilization rate of the hardware, we're going to increase the utilization rate of the software, right? I mean, that's one of the reasons why Epic is actually kind of important, right? People are finding that with a single socket server, I'm able to do what I used to require 2 sockets to do. So it's not only the additional hardware cost that they're saving on by not buying the second CPU, it's the additional software licensing costs that they're saving by not paying 2 software licenses because I got a dual socket server going on, right?
Yeah, with that, I absolutely agree with you, and it's clear that virtualization is going to live on at least for another decade. But I was just looking more at, and even what you said with Epic, the amount of CPU cores is increasing all the time, and we will certainly get to a point where software vendors may reconsider their licensing policy.
I think that eventually they're going to have to because of the way that things are changing. I agree, and we want to be a catalyst for that, right? We want to help the industry get there. And the other argument we get a lot of times is, well, won't this, make you sell less because you're more efficient? Because you can do in 1 rack now what you used to do in 2 racks? Well, we made the same argument about hyperconvergence and virtualization, but when we deployed those technologies, we actually ended up selling more. We gave customers new tools, new methods, new ways of doing things, and we were able to solve new problems for them. Right? So guys, this is what a fully disaggregated stack would look like, but there's a lot of environments where customers don't want to disaggregate everything. We have brownfield deployments, and this is one of the things that we're working on with the Dell team, is there's a lot of infrastructure out there. People have bought a lot of servers, and they say, you know what? I need GPU capability now. I don't want to throw away all my servers. What do? We say, no problem. We'll sell you a JBOG, box full of GPUs, connect it to our fabric, connect it to your existing servers, and come in with software and give GPUs to now the environment that needs it, right? So this is a way for us to augment existing infrastructure with new capability, right? Leveraging, again, composability, right? And this is the GPU one. Same thing is happening with storage. We have customers that say, I bought a bunch of Blade servers, and now my Blade servers are out of storage. I need more storage. I prefer to have direct connect storage because I need the performance out of those very expensive devices. Can you help me? Say, no problem. Sell you a box of NVMe drives connected to our fabric, connected to your existing infrastructure, and come in and give additional storage capability to your current environment. A lot of times we get asked, what's the benefit of composable networking? Why would I disaggregate my networking cards? All of my servers have networking inside of it already. And this is not a very common use case, but we do have some service providers who said right now, so we can put 24 network cards in a box, in a tray, connected to our fabric, and then dynamically assign those networking cards to any server that needs them. 8 of those networking cards can go to network A, 8 go to network B, 8 go to network C. If I need to move server A from network A to network B, how do I do it? I'm not going to go move cables. We just take the network card from network A and give it to the server that needs it, or take the appropriate network card, connect it to the appropriate network, and assign it to the server that needs to be on that appropriate network. So this is the benefit of flexible networking. right? We talked about this. User defined is the starting point, right? The user comes in and defines the machine how he wants it. The next evolution is obviously policy-based management. There is a time domain management, right? At this time of day, take this action. There's a usage or utilization-based management. When my storage goes above this rate, take this action. There's a failure-based domain, right? So when that node panics, I can detect that that node panicked, and I can take all of his SSDs, his GPUs, even his boot drive, and migrate it to a hot spare. Just because I lost the node, or I lost a DRAM module on that node, I haven't lost all of the devices that were connected there, because we can detect that failure, reprogram the fabric, and move those devices to where they need to be. So, as mentioned, right, we fully expect higher level orchestrators to be pulling the strings of our fabric. One of the projects that we have kicked off already is around Kubernetes Orchestration, allowing the Kubernetes engine to come in and dynamically reprogram the hardware based upon the policies that are set at a higher level. So whether, as mentioned, Kubernetes, OpenStack, Puppet Chef, we're going to integrate into all of those higher level orchestrators, right? We're not trying to come in and tell these data center admin that there's a new orchestrating tool that they need to use in order to get the benefits of Composable. We want to enable their existing software tools to be able to leverage this capability.